Now, what is left to do is to extend the bivariate case and everything we did before to an arbitrary number of random variables, but that's just merely putting pieces together. If we have more than two random variables, we usually stack them together into a random vector, and this random vector is then denoted by a bold type letter, like this X. And a random vector is nothing but a random variable, just that it doesn't map to R, but to Rn in this case. And we can apply CDFs and PDFs just like in the bivariate case, just that instead of two random variables, we now have n of them. And the exact same thing we can do, for example, for the expected value. So instead of having a function from R2 to R, we have a function from Rn to R, and the same techniques apply. So we weight the function value g with the density value, and then we integrate over all dimensions. So this single integral sign means that we integrate n times, like as indicated back here. And now we maybe want to extend this notion to other functions than scalar functions. And if we have this, we do this in the most simple way that we can come up with. So what we do is we interpret g as a stack of functions g1 through gm, and then we apply the expected value that we know from up here down here in every single component. And that's how we can get vector valued expected values. So there is one issue in the multivariate case, and that is independence. Independence cannot be generalized straightforwardly. Why? Because it does not suffice that the joint CDF of these n variables decomposes. And it also does not suffice if every pair of random variables, if you have n variables, is independent. But this has to hold for all subsets. So if you take 3 out of your 10 variables, then the joint CDF of these 3 has to decompose. And if you take 7 of them, this has to decompose. And this holds for every subset of your random variables that you have. And it can be either the PDF or the CDF that decomposes. And because of this slightly more complex notion of independence, it's sometimes also called the mutual independence, as opposed to the pairwise independence. The pairwise independence only claims that each pair of random variables, of your set of random variables, is independent. And here's a small example why this might be important. Consider the case where you have a coin and you toss it twice. And there's a random variable that models the first coin toss, and there's a second random variable that models the second coin toss. And you would have this IID assumption, that is, they have the same distribution, but they are independent. But now if you introduce a third random variable that measures whether or not they show the same symbol, so whether the first and the second coin had both heads or both tails, then all of a sudden x1 and x2 are no longer independent when this third random variable comes into play, because now if you know that the first one was heads, and if you know that both show the same, then all of a sudden the distribution of the second coin changes. Namely, you have a 100% certain outcome that the second random variable was, or the second coin toss was also heads. So they are not mutually independent. They are only pairwise independent. We can also extend the notion of variance and covariance to the multivariate case, in the case of random vectors. And if you have a random vector, bold x, The corresponding covariance matrix is the following square matrix. So we have an n-dimensional X and it's an n by n matrix, and the entry ij of this matrix sigma is simply the covariance between the scalar components xi and xj of our random vector bold X. And because covariance is symmetric, the matrix is also symmetric, so this means that sigma equals sigma transpose, that's the symmetry. And the positive definiteness means, if you don't recall this from your linear algebra course, this means that if you have x not equal to 0, then x transpose sigma x is greater than 0. That means positive definite. These are two properties that you can prove if you want to. The covariance also has some connection to the variance of the univariate case, because instead of defining it element-wise as we've done here, we can also define it as an expected value like we did in the variance case. And remember, the variance of a scalar random variable x was just the expected value of the centered random variable, that is x minus ex, and this squared. And this is what happens here. So we have x minus the random vector minus its expected value here and here, and we multiply it by its transpose. And in the scalar case, the transpose is just the same as the number itself, and that's why you get the squared. And here you get this x minus ex times x minus ex transpose. And that's the connection between the covariance matrix and the variance. Finally, we are going to try to get some feeling for multivariate distributions by looking at two particular distributions. Again, one discrete and one continuous one. And the discrete one, the first one, is the multinomial distribution. And the multivariate version of the binomial, that's what the multinomial is. And it also has two parameters, n and mu. We remember this from the binomial case. The difference is that here mu is not a single scalar, that is the success probability, but it's a vector of probabilities. They have to sum up to 1. And each of these entries of mu is the success probability for a special class or event k. So we have mu k, and this corresponds to the event k. And then we draw n times independently, and instead of 2 outcomes in the binomial case, in the multinomial case we can have k outcomes. And we have some restrictions. The probability mass function here is not defined for all x, but only for those x where all the components add up to n, because of course we have n trials. And this n choose x1, x2 up to xk, that's an extension of the binomial coefficient. It's the multinomial coefficient, and the definition is quite similar. And here you can try to analyze and to derive why we have these expectations, variance, and covariances. The most interesting thing is an example of when the multinomial distribution can be applied. Imagine an urn, or I prefer to consider boxes rather than urns. I think it's a bit macabre. If you have a box with n balls of k different labels, then if you draw a number of times with replacement and probabilities the number of balls of class k over the total number of balls, that's n, then the multinomial distribution applies. And also, we talked a lot about marginal distributions. If you marginalize out all random variables or all components of the random vector except for one, then your marginal distribution for the remaining component is a binomial distribution with the respective parameters. So the last distribution we are going to look at is the multivariate Gaussian, which is a straightforward extension of the univariate Gaussian or normal distribution to the multivariate case. Recall that in the univariate case we had a scalar mu and a scalar sigma squared, which were mean and covariance, the parameters of the Gaussian distribution. Now we do the exact same thing, except that we have a mean vector of k dimensions and also a covariance matrix which has to be positive, definite and symmetric out of the k by k matrices. And then you get this density function, and if you try to compare this to the scalar case, it's more or less exactly the same. If you assume that the dimension k is 1, you end up with the exact same density function. Just a couple of things here. This k sometimes slips through your hands when you're working with the multivariate case, and also this here is the determinant. In the scalar case, the determinant is just the number itself, but the determinant you will know from linear algebra. And then we know that the expected value is mu, we chose it that way, and variances and covariances can just be read out of the covariance matrix. And again, if we marginalize out all components of the random vector except for one, except for xi, then the marginal distribution of xi is again a normal distribution, now a scalar one, with a covariance of sigma ii. That's the ith diagonal entry of the covariance matrix and the ith entry of the expected value of the multivariate Gaussian. Multivariate Gaussians are extremely useful. In fact, they are so useful that we are going to dedicate a whole extra lecture on the multivariate Gaussian and its numerous nice properties for machine learning. Now we're almost done. One last note on notation. Consider these two expressions. The probability mass function of the random variable x evaluated at x versus the probability mass function of x evaluated at y. So this is about the only case that you can come up with where you would explicitly want to state that the probability mass function belongs to x because you're evaluating it at y. But apart from that, having these indices is very tedious for notation. So what we're going to do from now on is that we're going to skip these indices. And if you write px, this always means pxx, unless stated otherwise. If you want to have px of y, we're not going to write p of y, because p of y for us is going to be p y y. And only in that case will we return to this notation. So don't get confused with notation, we're just trying to make ours and your lives much easier.